Good afternoon, ladies and gentlemen. Welcome you all to the I²CNER seminar. This afternoon, we are especially honored to have with us Professor Susumu Kitagawa. Professor Kitagawa is the founder and world leader in the field of porous coordination polymers, which is now one of the most attractive and exciting and influential field in science. It is my great pleasure to introduce Professor Kitagawa to the university. Professor Kitagawa received his Bachelor of Science, Master of Science, and PhD in hydrocarbon chemistry from Kyoto University. Following the PhD, he joined the Kyushu University as an assistant professor and then associate professor. In 1992, he moved to Tokyo Metropolitan Universities as professor. And in 1998, he has been a professor of Kyoto University. And he is also now deputy director of Institute of Integrated Cell Material Sciences, that is WPI program of Kyoto University. For his outstanding achievement during his career, he was awarded many prizes, but I introduce only recent ones. In 2008, he received Alexander von Humboldt Research Award. In the same year, he received the Chemical Society of Japan Award. In 2009, Lectureship Award for Frontiers in Chemical Research, Texas A&M University. And last year, he received Thomson Reuters Citation Laureate Award. This award, according to my understanding, is only given to the scientists of Nobel class. I believe, and I think you also believe that Professor Kitagawa is clearly a candidate of Nobel Prize in near future. Today, he will talk about chemistry and application of porous coordination polymers, metal organic frameworks. Now, Professor Kitagawa, please.
Thank you very much, Katsuki Sensei, for very kind introduction. Yeah, I appreciate your introduction. And also Murakami Sensei inviting me to this the very prestigious institute. Also very recently, I'd like to congratulate this kind of great success to getting this kind of program. But anyway, let me start. This building, this is our building. We also have the WPI program. We call this is the iCeMS. This is just a fusion of cell biology and the material sciences. As you know, the iPS cells, stem cells, the Yamanaka, differentiate this kind of these cells by using the 4 genes, but still we have the big risk to have a cancer. And we think our material scientists try to have the new kind of chemicals and to apply this field for a very nice future. But anyway, and in order to develop this kind of material sciences, we have to have the very important field. That is the creation of a new stem cell technology and creation of a new mesoscopic technology science. Mesoscopic, not nano. We are chemists very familiar with the nano because the size of a molecule is just a nanometer. But we are very much interested in this kind of the size, mesodomain, because in the cell, there are so many molecules, of course the protein, genes, everything, and it has a kind of supramolecular states. But at room temperature, we have the Brownian motion. It's very difficult to control the single molecule function. But as the assembly effect, we have the very, very special functions in the cell. So this kind of the event occurs in the mesodomain. So what happens in the mesodomain? This nanoscale, just the issue of quantum physics. But in the case of the large scale, this is just classical mechanics. But in the mesodomain, we have the fluctuating world, the time-dependent, spatial, temporal event occurs. So we are very much interested in this kind of field. And in this field, also our compound, small, tiny compounds. But this has very special functions. Today, I try to talk about this one. Anyway, this is my compounds. Please look at this kind of the framework. It's very, very simple, just framework. So please keep in mind framework. Don't concentrate on the molecule. OK. So before I talk about my recent results, just I want to express my thanks to our collaborators, Uemura, he's associate professor in my department, and the assistant professor, Horike, and also in our iCeMS, we have also the associate professor, Furukawa, and the Matsuda, and the professor Oba. He is now in the department of chemistry in this university. But last year, he joined our group. But anyway, and all the people contribute very much our chemistry. But anyway, let's show you. 2,400 years ago, there was a thinker, a kind of philosopher in China, but in other words, in the Oriental. And he said, "Muyono" in Japanese, the usefulness of the useless. His name is Chuang-Tzu, Soji. And the meaning is everyone knows the usefulness of the useful, but no one knows the usefulness of the useless. Do you understand? Very complicated, looks like. But this is just a philosophy of the Orient, Asian wisdom. But anyway, so nothing. This looks like the useless. But if we focus on the chemistry, I mean the molecular field, molecular world, this must be a space for molecules and ions. So if we think this is very useful. At the end of my talk, I hope you understand this saying. So space is not a simple void, but an entity with functionality. This is background of my chemistry. Why so interesting? For instance, in the small molecules, ions are confined in the small space, but surrounded by the molecules and ions. So we have many chances to discover the unexplored phenomena and the structure also, and the stress phenomena, and very important for the chemist is the catalytic function. What does chemistry of space provide us? Dream of mankind. Important thing is the science and technology should use the abundant resources. That is modern alchemy. But there was a pioneering achievement early in the 20th century. All of you know the Albert Einstein, his great achievement, but very difficult to know this kind of persons. They are the Haber and Bosch process. He created the ammonia from the nitrogen in the air. Nitrogen, abundant materials, occurs everywhere. Very democratic. This is very important. So that is a primary period of alchemy of air. But problem is, this is big problem. This reaction occurs at 500 degrees C and 280 M. Very energy costly, energy consuming process. So nowadays, we are now in the just another alchemy aware. So we have to do this. This is very important. Why so? In Japan, lack of resources. This is very big problems. What's the future? We must use the abundant resources. So this means we have to develop this kind of chemistry. Of course, in the hydrogen, very important. This kind of gases are very, very important gases. For instance, in the space, this is just a space. And the natural resources, of course, and the environment, and energy, and life. Even for life, this kind of gas is very, very important. So the science and technology of gases, this is the very important keyword in the field in this century, I think. In order to do this, that is the second period of alchemy of gas. We have to manipulate these gases very freely, very easily. For that, separation is very important, and also storage, concentration for the reaction, also conversion. So we are standing at the side, the current chemistry, current science, still we don't have this kind of the nice the achievement. But anyway, this is my motivation. So today I'll talk about a little bit, a kind of progress in this chemistry. Unfortunately, I cannot tell you all about this. If I can do this, you do nothing. Okay? But anyway, we focus on the chemistry of coordination space. That is the chemistry I'm focusing on. How to construct this kind of the framework. This occurs in the macro scale. My students like to construct this kind of the framework. Very easy. Needless to say, but this is just a magnet instead of the metal ions. Or this is organic ligands. So we carried out this kind of chemistry in the flask. What is the key in this case? That is coordination bonds. Coordination bond is weaker than covalent bonds, but stronger than hydrogen bonds. This is the key for this kind of chemistry. By using this, you have the organic ligands and metal ions in the flask mixed at room temperature at ambient pressure. In a minute, you can get this kind of the framework. That is the micron crystalline materials. The size around the 1 micron to the 500 microns, very small. But you can get this. This is just the assembly process. And the macro scale, we have the block game and Lego. But in the nanoscale, we carry out this kind of the chemistry. So once again, this framework, you see, this is just a square grid-based framework. The metal ions here and organic ligands. What is interesting in this case, for instance, even if you have 1 micron crystal, the size of this channel, cross section, is about 1 nanometer. So this means you have 1,000 channels and 1,000, totally 1 million channels in a minute. You can get it. So what is important is we synthesize this at room temperature and ambient pressure. So this means you can use this compound at ambient pressure, ambient temperature, not raw temperature. The structure is just like this. You see, this is a ligand. It looks like a construction. But anyway, the gas molecules accommodate in this way. There is a strong interaction between the gas molecule and the surfaces of channel. So what about the history of this kind of chemistry? So this is a sort of the coordination frameworks. The coordination frameworks have been already obtained in 1936. The name is Prussian blue or Hoffman graphite, already obtained. But in the case of metal organic framework, in the case of Prussian blue, the ligand is cyanide. It's not organic. But this case is organic framework. So I was surprised that the Japanese chemists synthesized this type of framework in 1959, determining the crystal structure. This is very beautiful framework and accommodated the anions. But problem is very difficult to remove the anions. So at this moment, there are no concepts about the porosity, just the class-related compounds. Porosity is a very important concept in this kind of framework. Because mostly they are the first generation compound, we call this. Nature abhors a vacuum, in this case. So once the gas molecule are removed, the structure collapses. But you have a chance to get this kind of one. So we call this is porous coordination polymers. And over 10 years ago, we synthesized this type of frameworks by using the very simple molecule, by pyridine and cobalt. This gives a linear chain linked by another linear chain to give this kind of motif. This motif gives a crystal. There are channels, spaces for the gas. So we carried out this pressure, we carried out the gas absorption for many times. So this means this compound has porosity. Also, in the United States, Omariagi carried out this kind of experiment by using the zinc compounds at low temperature in this case, but still they can obtain this kind of reversible absorption. So we call porous coordination polymers or metal organic framework. This is coined by the Omariagi in this paper. But anyway, whatever we say, this is just a compound having a porous structure. So this is just a statistics in published papers, and here now in the over 2,500 papers published, including the proceedings. So many researchers are interested in this type of compounds. Why so? The conventional materials here, the inorganic materials and carbon materials, as you know. But in between, we have this kind of new type of compounds because they have the high porosity surface area. They have uniform structure because they are crystalline state. And we can design this framework. Very convenient. So there are two concepts, very important concepts. Robust porosity, very stable, and soft porosity. This is a new type of concept. So we understand about this because of their zeolite. So we focus on this one today. In the case of the soft porosity, we classify these compounds for the third generation compounds. That is responsible to the gas molecules changing their structures. So we call soft porosity. So what is soft? We call this is soft porous crystals. They have the soft porosity, and they are single crystals, transformable forms, one crystal form to the others. They have porous frameworks. Of course, there are so many compounds they call the soft matters, but this is completely different because this has the regular structure, crystal compound. This is the idea how to synthesize this type of compounds. The first one, you have this flexible ligands. For instance, the organic molecules have a flexibility. Even if you have the rigid framework like this, jungle gym structure, there are interpenetrated structure. So this means mutual dislocation gives a kind of space. The other one is a layered structure. In between the layers, you have this kind of the space for this. Another type is, this is just a toy. So push one side, abruptly you can change this kind of volume. This is also another type. By using this, we have a different type of the functionalities, storage, separation, polymerization, and so on and so forth. I want to introduce you the several about this. In particular, the separation is very important. This is just an example about highly difficult separation pairs or the groups. For instance, in the acetylene and CO2, the size essentially is the same, and the boiling point is very similar, very difficult to separate these gases. The other things, the flue gases, the CO2 has the higher temperature, boiling temperature, but still the difficult to separate without the high energy. So on and so forth. Okay, let's go to have this separation. So almost 6 years ago, we synthesized this type of compounds constructed from copper and by pyridyl dicarboxylate and by pyridine. And here, this shows this kind of sorption. But in the case of this is activated carbon materials. The CO2 and acetylene sorption profile like this, pressure and adsorbed amount here. Difficult to see the big difference, but our system is here. This case is high pressure, but this case is very, very low pressure. Already the acetylene saturated in this case. What happens in this case? So we determine the crystal structure. This is the crystal structure, one of the channel. This is a channel here. The acetylene accommodates in this way. And there is a hydrogen bonding interaction between the acetylene, hydrogen, and the oxygen. This is the ligand constructing the framework. What is interesting is there are double hydrogen bonding system. This is very useful for this kind of sorption. So what happens in this case? Okay, this is the diffraction patterns. We observe the initial structure and also the initial structure and the final structure. And we also the intermediate phase. So we determine the crystal structure. That is the result. This is the direction of the channel. This is the pillar ligands. And so this is a vacant form, and 70% acetylene accommodated. So this is 70% this occupancy here. And then this is 100%. You see, this is the volume here. And first, the structure expand to accommodate acetylene. And finally, shrinkage occurs in this case. Why so? Because the framework want to have a cross-pack interaction for the acetylene. So first expand, finally shrink it. This is the mechanism. And the another thing is this pillar ligand rotate this direction to the other one. So this is a kind of a small flexibility in this case. Another things, just I showed you before. This is the layered systems. And the reality is like this. For this kind of the air gas. The structure synthesized by copper and dihydroxybenzoic acid and by pyridine. Copper and by this ligand gives a layer, the pyridine gives a layer, and this has this kind of the pillar ligand, pillar. But no strong interaction, I mean the covalent bond, no covalent bond. So, removing gas molecules, and then apply the gas pressure at room temperature. This is the nitrogen, and at this point, the abrupt adsorption occurs in this way, and dissolve here. We observe the hysteretic sorption in this case. So we call this is gate opening pressure here. This is a powder microcrystalline sample. We apply the pressure. The structure expands to accommodate gas molecules. What happens in this case? Still, we want to know what happens. We use the synchrotron radiation facilities to observe it, but not succeeded. But anyway, this is just my imagination. Do not believe this. in the future, maybe different aspect, but more or less, this kind of the change occurs. Okay? What is interesting here, carbon, CO2, methane, O2, nitrogen, all the gases gave different type of gate opening pressure. The supercritical gas is very difficult to recognize this kind of gases at room temperature. But these materials does. So the other kind is the natural gas, biogas. Methane, CO2 are like this in the, just I showed you this kind of, the same things. And the methane and the CO2 like this. But usually, the industry use this kind of pressure swing adsorption process. Pressure swing means the pressure, higher pressure and reduced pressure. So the pressure range is 0.4 to 0.7, because in these regions it takes more energy to remove the gas molecules. So this is very important. But you see, CO2 cannot get removed in this region. It's not a good way. We have to change the gate opening pressure. How we can do this? We are chemists. We change this ligand, okay? We replace these ligand from this one to the other one. What happens in this case, we observe this. You see, CO2 almost in this region. We can change the gate opening pressure by chemical substitution technique. We are very happy. But more or less, and in Japan, this is all the energy consumption statistics. You see about 34% for the chemical industries. Chemical industry use energy for the separation about 40%. So this means over 10% of total Japan energy for the industry is used for the separation. Very time and energy consuming process. So separation is very important. So let's go to see the separation process about the flue gas. One way to use this is a very authentic idea. This is the kind of framework having the stronger interaction site for CO2. So Jeff Long synthesized very, very useful framework system. The very high affinity for CO2. It's very good, but problem is, how do they remove CO2? Reduce the pressure by very, very low in high vacuum condition. Energy consuming process should be used for these materials. So we synthesize this framework just like this. Zinc ion gives, by using this ligand to give a ribbon. Ribbon gives this kind of the layer by using the bipyridine. And the bipyridine, and this layer gives a stacked structure like this. Okay? This is the framework. What is interesting here, there is interaction between the layers. This is the ligand here. So we can change this site from this one to the other in this way. So we can tune the interaction for the different type of absorption. Like this, we determine the crystal structure. And please look at this one, CID3. This is used, the naphthalene substituent is used for the structure here. And the small channels here right now. And this is just a single gas absorption profile, N2O2 CO2. It's not so good because the difference is not large. Okay? When we compare the zeolite, the capacity, this is the champion with NAX. This shows the very sharp adsorption for the CO2. So most of the audience judge the results. Oh, this is much better than this. Because the interaction between the CO2 and the surface, this energy is 49% but this case is 30 kilojoule per mole. Oh, this is okay. But the problem is, very high affinity means we need to have higher energy to remove gas molecules. This is a big problem. Okay, we carried out the mixture of gases. Our compound here, 1:1:1 mixture. This is the initial the mixture ratio, 1:1:1. But in the cavities, only CO2 adsorbed 99%. Zeolite also 97%. Selectivity is very close to each other. Why so? Our compound shows the single gas adsorbed like this. But in the case of mixture, CO2 is preferentially adsorbed. Maybe this has a kind of flexibility. So like my hand, so this molecule, this framework can trap the CO2 preferentially, maybe. Still the missing, but anyway, in the case of the activated carbon, the selectivity is 10 to 15. This is a rigid, robust framework of MOF, or metal organic framework, in that case, 4 to 6. And the highest one is 20 to 27. Our case is 39. We can increase more. So flexibility is very important. Oh, this is just a kinetic case in the just 1% mixture of CO2 in this kind of gas. We can selectively remove the CO2 from these gases. Anyway, so the flexibility, the soft porosity is very important concept, and also the very important property for the separation in the other functions. So this is just an idea. Today I show you I distribute the Xerox copy of the reviews. But anyway, most of the people, the researchers ask me, you synthesize this kind of framework by using organic ligands and metal ions. You can synthesize the environment responsive framework. So I try to synthesize that. So then the light and electric field, magnetic field, and heat and pressure. So the time is limited. Just today, I want to show you about the charge. The keyword is charge. Keyword is the charge. That is very interesting. And so let's go to the new type of compound having soft porosity and charge. So we have chosen the TCNQ, very simple molecule. And by using this, we synthesize this type of framework. And but accidentally, we obtained this framework from the dimer of TCNQ. So TCNQ is famous about the electron withdrawing molecule. But in the case of dimer, this is TCNQ2 minus. This is very famous about the donor of the ligand electron. So the channel shape is like this. The synthesis is very simple. Zinc and the TCNQ anion and bipyridine gives this kind of the geometry of zinc and the channeling structure. But looks very complicated. But please look at this one. This is a channel running from this side to this direction. So the narrower channel, wider, narrower, wider, narrower, running in this way, also perpendicularly. At the beginning, the benzene molecules are dissolved in this way. The YSO, there is an interaction between the CH pi interaction, pi time interaction. It's a very normal in the organic chemistry. But the mystery is like this. We carried out gas absorption. Most adsorbed gas, acetylene CO2, could not be adsorbed, but NO and O2 preferentially adsorbed. What happened in this case? So this is the physical parameters of these gases. Very complicated. So just I want to summarize this one. In the case of the kinetic diameter, this is the size of molecule. NO is the smallest, but the next one is CO2, but this could not be adsorbed. This parameter is not good. Next one is dipole moment. CO has dipole moment, but this is not adsorbed. Quadrupole moment, acetylene CO2 should be preferentially adsorbed. Not. Polarizability, no. So finally, this is just a calculation. But anyway, this is the capacity to the molecule can be reduced. So the only O2 and NO has a higher in this case, because this is the unoccupied orbital. So then we observe the Raman spectroscopy in situ, and we observe the value is 1454 wave number in between the neutral oxygen and the superoxide type. So, and over 10 years ago, most of 10 years ago, we observed synthesized this kind of oxygen sorption in the channel. So the value is 1561 wave number. It's a bit higher than this, but close to the neutral value. This is a neutral case, but our case is the Raman band show the smaller one. So maybe there is a partial charge transfer between this. So this is the driving force to absorb NO and O2. So by using this kind of framework, we can carry out this kind of new chemistry. The other things, this case is a charge transfer type interaction, but this case is another type. This is just a transport of the charge, in particular in the proton. So the background of this science and chemistry is very, very huge. So, but I cannot stay on this topic a longer time. But most of you knows because of fuel cell, many people are focusing on that. So our focus is just anhydrous the proton exchange materials. So we don't need to have the water. By using this, we can carry out this kind of materials and at higher temperature, higher than the 100 degrees Celsius. So our idea is like this. We need to have this kind of molecules in the cavities. So what happens in this case? So we have chosen the imidazole because imidazole has the tautomeric form, proton acceptor and donor. And of course, this idea is already found in the 1997 and before. So we want to use this kind of the proton conduction by imidazole by Gotta's mechanism. And in order to do this, we have to synthesize the new type of framework. And Gerard Ferret, synthesized very famous materials in MER53 by using aluminum and the benzene dicarboxylate. This is very famous materials, but we use, instead of this, we use the naphthalene dicarboxylate. So we determine this crystal structure. The capacity, the properties of the surface are completely different from this. This has the hydrophilic channel, but this case is hydrophobic because of this site. That's the point. So we accommodate the imidazole in the cavities, and then they are carried out. Oh, okay, this is the thermal stability in this case. The over 100 degrees Celsius, still the imidazoles are accommodated in the channels. Of course, we can carry out the different type of imidazole derivatives. So we can extend more. Very recently, we get more good data, but sorry, today I cannot tell you about this. And anyway, and this is the conductivity of this type of compound. And after the 100 degrees Celsius, still this is increasing more and more. This is very important. And we observe the NMR spectrum and so on and so forth, and we characterize what happens in the case of imidazole. So imidazole in the channels have a sort of the, not strongly trapped, a sort of the freedom, in the motion of freedom in the channel. That is a key, but if the channels are very large, imidazole molecule accommodated, many imidazole accommodated, in that case, it does not work. So it's a very subtle issue for the higher conductivity. But anyway, we succeeded in this kind of the results. Okay, and this topic is also very important in the soft porosity and light. So the time is limited. Just I want to introduce this one. This is also very useful, but the time is limited. This one, and we try to have very reactive surface in the channel, but of course very difficult if we use this kind of reactive one at the beginning of the synthesis. So our idea is to use a dormant precursor. We use precursor, and synthesize the framework, and then irradiate it and obtain this kind of the framework. This is our idea. What kind of species introduced in the channels? So our idea is like this. So we call this is reactive open shell atom, ROSA. And we use this, first we use the azide. And from azide to nitrogen is very important. So in order to do this, please look at this ligand system here. Yeah, we use this one for the synthesis of the structure. The idea is that zinc is used for framework by using this one, and tape are linked to give a layer here, two type of layers, with respect to the direction of the azide group, and the stacked structure like this. This is just a crystal structure here. So the relationship between the azide group is like this. The distance is 3.4 angstrom. There are no strong interaction between this. That is very important. And then we irradiate by UV light this type of compounds. By irradiation, the nitrogen generated. So what happens? We observe the crystal structure in situ type in the crystal structure. This is the result. Framework here. This is the nitrogen. Of course, the disorder in the 3 site. But this is the nitrogen. As you know, Katsuki Sensei knows, of course, and the organic chemist knows, the very reactive. Impossible to maintain this species. But this is stably maintained, this site. Because the distance between the closest distance is 4.2 angstrom. No chance to have a coupling reaction in this case. So fortunately, we obtain this kind of very reactive one. And we try to have the oxygen absorption. This is the initial system, okay, precursor. Of course, oxygen cannot absorb in the cavities. Then we irradiate in the presence of the O2, we irradiate this materials. But please look at this. And when irradiate this, the nitrogen generated, and then in the presence of CO, this gives the NCO. This one gives NO2 or NO. So this is the result. In the 50%, the yield of the nitrogen, in that case, adsorption like this. In the 100% case, the oxygen is absorbed. Even for the very tiny oxygen in the gas systems, the only oxygen trapped in this case. So this is just idea for the removing trace harmful gases. you can put this type of crystals on the surface on the something, and the close it, they irradiate it, so the only oxygen or CO absorbed in that case. But the other thing is just idea. You can put the various type of the organic ligands to decorate the inner surface of the channel. But anyway, but this is the other case. So I have to close my talk, but this is also very important. And many people ask me, okay, this is bulk crystals. Can you get this kind of thin layer, thin crystals, and the nanorods, and so on, so on? Okay, so just I want to show a bit about this. So this is the coordination framework. This means coordination, okay, phenomena occurs in this way. So coordination is like this, equilibrium. The surface should be equilibrium state. So in order to carry out this experiment, please look at this crystal. This dicarboxylate are linked layers. Layers are linked to this violet ligand to give this kind of the structure. This is the nitrogen surface. This is the carboxylate surface. So there are 4 carboxylate surfaces and 2 nitrogen surfaces in this case. So my collaborators are very smart, and usually by using these components, we obtain the bulk crystals. There are many defects. Also, of course, we can get the bulk crystal. But in the presence of the another ligand, we call modulator, coordination modulator. Modulator stops the extension of crystal growth on the special surface. This is the point. So we use modulator to obtain these nanoparticles, nanocube, and then nanorod. This is the idea, and also obtain the results. And the ions are linked by the yellow one. This is bidentate, extend more and more, but using the modulator, we can stop the growth of this surface here. But still this site have a chance to give this kind of the crystal growth. So we can control this kind of the size and the shape by using modulator. This is completely the chemical process. And this is just one of the results here, the nanorods here, we obtain here. And what is interesting, in the case of the gas absorption here, this nanorod has a higher capacity than this one, because the modulation method is very, very careful method to crystal growth. So the defects, the number of defects are very, very small. Another idea is also in collaboration with the German group, they have the reverse microemulsion, because emulsion has a small reaction field. So by using this, we obtain this kind of rod in a very short time. And of course, the size is very short, so diffusion of gases is very fast, of course, in that case. Okay, so mostly we can control the size and shape in the future. This is one of the examples, but in the future we can go this. What about the surface? Only surface is possible. At the beginning, I showed the structure. The surface like this, because this is the ideal one, very beautiful. But you see, the ligand can have a chance to stand on this side. So my student on this idea, we synthesize this kind of the core shell type crystals like this. One component is just we use the zinc, But this pillar ligands in this case is just a naphthalene dicarboxylate. In this case is DAPCO here. The different type of the ligand system here. Synthesis is very easy. Even physicists can do this. Yeah, okay, and the solvothermal synthesis, and first you obtain the crystals. And then these crystals are put in this kind of solution containing different type of ligands, and finally obtain this. And this is characterization by using microscopic IR spectroscopy. We observe this site, this site. So you see, the zinc framework, the shell crystal has this framework, and the core crystal has the same one. So we determine this one. Also, the crystal diffraction is also gives this kind of the structure. Very beautiful one. So whatever the size and shape, we obtain this one, this type of crystals. So the question is, for what purpose do you synthesize this type of compound? There are many, many ideas, but this is very hot data, and very recently we obtained this. This is just idea, and the selective storage. So this means the capacity, store capacity is very high, but this has the cover, jacket of the separation. This one is reaction. This one is a sensing something. So this is just an experiment for the branched alkane and the linear alkane. Linear alkane has a smaller the cross section. So if this crystal has a jacket having the smaller aperture of the channel, this could be selectively adsorbed, but this is kicked out. So we synthesize these compounds by using this one, and this is naphthalene or anthracene dicarboxylate. This is the outside. This is the inside. So the crystal structure showed core has this kind of channel here, but in the shell crystal, the jacket has a very small channel. So by using this, we carried out the cetan and isocetan here, and we obtained this data here. In the case of core shell crystals, only cetan adsorbed. But of course, if we have a very small channel, of course the cetan is adsorbed. But the problem is, size is very small. It's very difficult to have a large amount of cetan adsorbed. But anyway, this is the result. So by using core shell crystals, we can carry out many, many things. But anyway, this is just idea. So many, many researchers are focusing on the single properties of this type of compounds. But in the future, we will have the integration of this kind of pores, because these compounds are synthesized from the organic molecules and metal ions. We can design at the beginning of the idea. So this is very important. So separation, response, reaction, and so on and so forth, by using this type of the morphology and the clarification about these channels. Okay, I have to finish my talk, and I want to thank the many coworkers and also the funding agencies. Without this kind of big funds, I could not carry out this science, chemistry. Thank you for your kind attention.